Okay, I think we can start with it. So thank you very much for being here. Today we have Alfonso López Aguerri, special guest this week. And he studied in Zaragoza. He's from northern Zaragoza, close to the Pyrenees. And then he did the PhD in the IEC, postdoc in Basilea, and then came back to the IEC, where he's now. And today he's going to talk about the evolution of low mass galaxies in the nearby universe.
So, thank you very much. It's a pleasure to be here and give you a brief summary of what I am doing in the last year about the evolution of galaxies with environment. So this is a typical picture from Sloan about the distribution of the galaxies in the nearby universe. And you can see that the distribution of the galaxies in the scales of megaparsecs is far from being uniform. Okay, there are several structures that, if you do a focus in this region, you can see a variety of different structures, filaments, clusters, galaxy symbiotes. Okay, with very different physical conditions. The evolution of the galaxies. Here we can see, for example, as an example, galaxies living in voids in the field. These are basically 20–30% of the galaxies in the universe. Then we have galaxies in small groups going down through the filaments to the galaxy clusters. In groups, we have about 50% of the galaxies, and then we have the big monster, the galaxy cluster, where thousands of galaxies are interacting each to each other and evolving at the same time. And about 20–30% of the galaxy population is located in these galaxy clusters. This is a picture in 2D when simulation helps us to see this picture, this nice picture, this structure in 3D. This is the Eagle simulation, and this is a travel throughout this large-scale structure in the universe. You can see here the filament connecting clusters. Here, this is a supercluster region, and then you have seen the filaments surrounding voids, big voids of almost empty material. Also, the simulation tells us that basically this is the mass distribution in the different structures in the universe. More or less, in filament we have 50% of the mass. Then we have the walls, 25%, the voids 50%, and the nodes, the clusters, only 11% of the mass of the universe. And if you see the volume, you can see that the voids is more than 3/4 parts of the universe. And then we have the walls, about 20% of the volume, the filament 6%, and only the cluster occupying just 0.1% of the volume of the universe, and where the big transformation of the galaxies occur. Okay, so the environment is influencing the evolution of the galaxies, and this is far known in different clusters, in different papers on the literature. These are some classical relations. For example, one is the relation between the morphology and the structure with the environment where the galaxies live. Basically, this is the morphology density relation discovered by Dressler in the 80s. You can see, for example, here that when you move to high density environments, the fraction of early-type galaxies is going up, and the fraction of late-type galaxies, of spiral galaxies, is going down. Also, there is a connection that we discovered many years ago between the scales of the galaxy, and especially the scale of the bright disk, and the position in different nearby clusters like Coma, Virgo, etc. In the sense that the scales in the center of the clusters are smaller than in the outskirts. And also there is a relation with the length and the scale of the disk dwarf galaxies and the location in the nearby cluster like in Virgo. But not only the influence is in the structure, the influence is also in the stellar content of the galaxy, the typical relation of the star formation as a function of the density discovered many years ago, in which when we move to high density region, the star formation, the average star formation rate of the galaxies is decreasing comparing with the field galaxies. Even more, there is a effect in the color of the galaxies and evolution with the redshift, the so-called Bacheloret effect, in which the fraction of blue galaxies is higher in clusters located at high redshift than clusters located in the nearby universe. Also, the gas content on the galaxies is affected by the environment. This is the typical result from Kayate et al. in the 90s, in which they discovered that the galaxies in Virgo they were anemic in gas. Okay, so similar galaxies located in the field has more gas than the galaxies located in the Virgo cluster. This is a recent paper 10 years ago or something like that about the H1 content of the galaxies in the Virgo cluster. You can see here the disk of H1. The disk in the inner region of the Virgo cluster are smaller than the disks located in the outer region. And this is a dwarf galaxy falling into the Virgo cluster, in which is saw this tail of gas when the galaxy is falling into the central region of the cluster. But not only the cluster and the high density environment of the galaxies affects to the galaxy population, also the large scale structure, the filament structure, also affect to the evolution of the galaxies. For example, the stellar color, the morphology, the star formation. Galaxies located in filaments are more massive, redder, and has a smaller star formation than similar galaxies located in the field, in the bodies. Here you can see, for example, the color, the J minus R, and this is another color, it's not here, as a function of the distance to the filaments. And you can see in this paper from Goodman et al., in which the galaxies, the color of the galaxies is evolving, getting redder and redder and redder when the galaxies are closer to the filaments. It's very clear for bright galaxies, brighter than -20. It's not so clear for the dwarf galaxy. Here, this is a recent work that we are doing with Stefano. This is a submitted paper in which this is the cumulative distribution function of the color of the galaxies and the star formation rate of the galaxies. Galaxies in the field is in blue, galaxies in filaments are in violet, in pink, and you can see that the galaxies in the field are a little bit bluer than galaxies in the filaments, and the star formation of the galaxies in filament is a little bit smaller than the galaxies in the field. Why is that? Why the environment or the density distribution of the galaxies influencing on the galaxy properties? Many different reasons, many different physical processes. One is the typical gravitational interaction, mergers, cluster potential. All of this is enhanced when the galaxies are located in high density environment like galaxy cluster. This picture, this movie here is showing the formation of one of the central galaxies in galaxy cluster, and you can see that there are a lot of interaction. So this interaction produce evolution in the properties of the galaxies. But not only merger, also fast encounters, harassment, what is called harassment, influence in the properties of the galaxy. But also there are in high density environment like galaxy cluster, there are also hydrodynamical interactions, okay? Stagnation, strangulation, gas stripping, all of these processes, what it's doing is sweeping the gas from the galaxy, which affect this to the formation of new stars. Here I show you some pictures about gas stripping, in which this is a gas disk falling into the cluster. This is the direction of the infall, and you can see that the perturbation of this gas, and the gas is swept out from the disk of the galaxy as it is falling into the cluster. Also, filaments are affecting to this gas. Basically, this is a scenario proposed by Aragon Calvo et al., in which several interactions or the inflow of the galaxies into big halos or the inflow of the galaxies into the filaments produce a detachment of the cold gas, cosmological cold gas from the galaxies, and this produces a quench of the galaxies when they are moving from the voids, from the field to the filament, and then goes to the galaxy cluster. Okay. One of the galaxies that can be affected by the environment are the dwarf galaxies. First of all, what is a dwarf galaxy? There are many definitions across the history. Hodge in the 70s, they say that the galaxies are small, of course, and with a small absolute luminosity and low surface brightness. Then Bingley in the 80s produced a better definition, a more quantitative definition, and they consider that the dwarf galaxies are those with absolute magnitude in V-band fainter than -18. Okay, so with this definition, dwarf galaxies are interesting because they are the most abundant galaxies in number in the nearby universe. What happened is that the dwarf galaxies, there are many different dwarf galaxies. The dwarf galaxies is a real soup of different galaxies. We have late-type galaxies, we have early-type galaxies. The late-type galaxies are quite irregular, with irregular structure, irregular morphologies, complex stellar and gas kinematics. Basically, they are located in low-density regions. And then we have the gas dwarf system, the early type dwarfs with regular shapes and found usually in high density regions. But early type dwarfs, and this is going to be my subject of this thesis, apparently they have no features, but this is not true because some of the galaxies, the observation revealed that they have structures like bars, spiral, discs, as the normal bright spirals. Okay, exhibit continuous relation from the giant to the bright galaxies, such as Puri-Fisher relation and so on. And typically, the stellar content basically they have all stellar population, metal poor stellar population with values of alpha enhancement around 0. And basically, with all of these ingredients that we have here, with the structure of the dwarfs, scaling relations, and stellar population, we have to put all of this together and answer the big question about the origin of the dwarf. Are they forming at high redshift and evolve passively? Or are they coming from star-forming galaxies and it's a consequence of the transformation in high-density environments, cluster groups, or even filaments? And this is the topic that I am going to explain to focus here. In order to do that, we select 4 galaxy clusters during the last years in the nearby universe with very different characteristics. Here we have, for example, the Fornax cluster, which is a very close cluster. With more than a cluster is a group because the sigma, the velocity dispersion of the cluster is just 370 kilometers, and the mass of this group is 710 to the 13. Then we have a bigger cluster like Abel 85 with a mass 2.5 10 to the 14. Then we have Hercules cluster, 4 10 to the 14, and we have Perseus cluster, which is the biggest cluster that we have in this sample, is 6 10 to the 14. This cluster formed 2 PhD theses. The Perseus, Abel 85, and Hercules was the PhD thesis from Irene Abuli, and the Fornax cluster was a recent PhD thesis from Jorge Romero Gomez, focused on the stellar population. I'm going to show you the main result that we obtained analyzing this. Well, the observation that we have, and I think this is interesting because what we did is take very deep spectroscopy on these 4 clusters. Very deep spectroscopy with different telescopes and different cluster different instruments. Okay. For example, for the Fornax cluster, we use the Anglo-Australian with the SAMI spectrograph. For the Abel, for the Hercules and Perseus cluster, we use the William Herschel with AF2, and for Abel 85, we use the BLT with BMOS system. In all of these clusters, we have thousands of galaxies, especially in these three first, of galaxies with velocities belonging to the clusters. We observe the cluster farther than 1 billion radius, and these are 100 of these 1,000 galaxies, 100 turn to be cluster members. Okay, this spectroscopy goes to a limited magnitude of -16 in all of these clusters, and in the Fornax cluster we were concentrated in the dwarf galaxies. Just focus on the dwarf galaxies with masses between 7.2 and 9.3. So the main topics that I am going to tell you basically is about, first of all, about the galaxy population in Abel 85, Hercules cluster, and Perseus cluster, and basically focusing on the luminosity and the color magnitude diagram. Okay, how is the dwarf population in this cluster? It's a population similar to the field. All these clusters have the same similar dwarf populations. And then in the Fornax cluster, we were focusing on the quenching of the dwarf galaxies, analyzing basically the stellar population properties of these galaxies. And basically, are the dwarf galaxies quenched by the cluster environment, or they were quenched in a different environment? So starting with the luminosity function. The luminosity function is a very simple statistic. Basically, the luminosity function is telling you the number of galaxies that we have per luminosity, basically. But it's very useful. It's a very useful statistic because we can compare the luminosity function in different clusters, or you can compare the luminosity function of population of galaxies at different redshifts, and you can see if they are different, if they evolve or what. Okay. 2 main ways to compute the luminosity function: the spectroscopic way and the photometric way. The spectroscopic way is very accurate, but it's very expensive to take because you need a lot of spectra, basically, to determine the velocity and to determine the cluster members. The photometric one is cheaper, use less telescope time, because you take a statistical subtraction of the sky pattern, basically. But it's not so accurate like the spectroscopic luminosity. Usually, the spectroscopic luminosity, the luminosity function, the galaxy luminosity function, is described by a sector function, which is this function here. This function has three parameters. This is the 0 point, phi star, m star, and alpha, and has 2 parts: one potential part and one exponential part. M star is representing the change between the exponential part and the potential part, and alpha is representing the slope of the potential part, the frame end of the luminosity function. When alpha is -1, the luminosity function is very flat. When alpha is smaller than -1, the luminosity function is higher in the low mass regime. What was known in the photometric luminosity function? This is a paper that was very popular in 2006, analyzing galaxies from Sloan. Opeso discovered that the luminosity function has a big upturn at the faint part in the dwarf regime. Okay, so you have the luminosity function, and then there is a big upturn of dwarf. There is a very big excess of dwarfs. What happened in the field? This is the luminosity function from the field, and you can see that in the field the luminosity function has no upturn. Okay, so this was interpreted directly because dwarf galaxies, red dwarf galaxies, is in the red population, this upturn, not in the blue one. Red dwarf galaxies are produced, are quenched in the galaxy cluster, basically. I tell you that this is the field luminosity function, and when you split the field luminosity function in blue and red galaxies, the faint part of the luminosity function is dominated by blue galaxies. In the cluster, the faint part of the luminosity function is dominated by red galaxies. Okay, so this was a result, and people said, okay, the red dwarf galaxies are connected in clusters, basically. What happened with the spectroscopic luminosity function? These are our cluster: Ability 5, Hercules, and Perseus. And these are the luminosity functions. Ability 5 has disappeared in the dwarf part, but Hercules not, and Perseus not. Okay, so it's not so universal. The after is located in some cluster like Ability 5, but not in the other. If we take the numbers, for example, the slope in Ability 5 is minus 1.47. The slope in Hercules is minus 1.1. The slope in Perseus is minus 1. It's completely flat. Okay. One more. If you split the luminosity function in red and blue, again, Ability 5 is dominated by the red galaxies. Okay? These are the red galaxies. This is the blue galaxies. So in the faint end, the red galaxies dominate over the blue galaxies. But if you go to Hercules, it's the opposite. In the faint end, blue galaxies are dominating through the red ones. And if you go to Perseus, they are more or less the same. Okay? So it's not universal, it's not so universal the fact that the red dwarf galaxies dominate the faint end of luminosity function in galaxy class. Some of them yes, but some of them no. And this is one question that should be explored a little bit more with more clusters, with a larger survey about luminosity functions. Okay, we did this in the simulations. We computed the composite luminosity function of the sea gold clusters. This is a project of 30 high-resolution zooming simulation of galaxy clusters. And the faint end is weakly, at least in simulation, is weakly dependent on color and mass, and so an after typically between minus 1.2 and minus 1.4, let's say. So here you can see, for example, this is alpha, this is M star, these are the observation, Ability 5, Hercules, Perseus, and in these lines is the closest cluster, let's say, or the most similar cluster to Perseus, to Hercules, and to Ability 5 in mass and so on, okay, from the simulation. So simulations can reproduce clusters like Ability 5, Hercules, well, more or less, but Perseus is very far away. Okay, Perseus is very far away. The observation, Perseus was the more massive cluster, and observation tell us that the luminosity function is flat. Simulations, the most massive cluster, the luminosity function is not so flat. Okay, this is the difference, basically. So it still is something that we have to work on. Okay, so the conclusion in this first point basically is that the luminosity function is, when you do the luminosity function spectroscopically, the luminosity function in galaxy cluster in the dwarf population is not so universal. Okay, Ability 5, Perseus, and Hercules has very different luminosity function. So I think still there are some question about is this different dwarf population in galaxy cluster due to different masses, dynamical status, cosmic wave, accretion, or what? So what is forming the dwarf population in galaxy cluster is still, I think, is still not well answered. I'm going to pass now to the Fornax cluster, and I am going to pass now to the analysis of the stellar population of the dwarf galaxies in the Fornax cluster. So in this work, we observe the Fornax dwarf galaxies using the spectroscopic instrument, the STAMI instrument at the Anglo-Australian. Here I show you one of the sample of the observations. This instrument has 12 mini IQ per 20, and the observations in each single galaxy were about 7 hours. We concentrate on 38 galaxies with masses between 10 to the 7, 10 to the 9, basically, and we collapse the visible spectra. We collapse the visible spectra in a large aperture, occupying more than half of the 50 of the effective values. Okay. Here I show you an example of one of the spectra. The instrument has two arms. One is the blue part and the red part. Here I show you the resolution, the full width, etc. So first, using LOD, we did the kinematics of the galaxies. And here I show you two galaxies. This is a galaxy with a very high signal to noise, and you see in red the fitted spectra, and in black the observed spectra, in the blue and in the red arm. And this is the galaxy with the lowest signal to noise. Here we compare basically the velocities in this work with the velocities in the literature that we obtain from this field. The velocities are very good. And here I show you the velocity dispersion in this work and the velocity dispersion from the literature. You can see that we have real dwarfs. We have galaxies with less than 20 kilometers per second in the velocity dispersion. Then we reanalyze, using the same methodology, we reanalyze the galaxies from Atlas 3D. Because the galaxies from Atlas 3D, they are basically a sample of 260 massive galaxies with masses between 10 to the 9, 10 to the 10, and 10 to the 12, okay? In the nearby universe. Then we did with the same methodology, we computed the velocity, the gravitational velocity, and the velocity dispersion, and we compare with the analysis that the Atlas group did for this galaxy with McDermott et al. 2015. And these are the results that we obtained fitting the spectrum. Basically, what I showed you here is the age and the metallicity as a function of the sigma, of the velocity dispersion, and as a function of mass. The black and open symbols here are the galaxies from Atlas 3D, reanalysis with our library, with our methodology. And the red points here are the dwarfs from the Fornax. So you can see, for example, in the age, you can see that most of the galaxies from Atlas 3D are very old, more than 10 years. But in contrary, the dwarf galaxies, the ages are a little bit smaller. Only 3 galaxies from the Fornax are equivalent to the very massive ellipticals in the Atlas. And also, this is the metallicity mass relation. Okay, the elliptical galaxies, let's say the massive galaxies, are located here, and the dwarfs from Fornax are located here with a higher dispersion. And these 3 old galaxies are quite out from the metallicity mass relation. Okay. Using Millet's library, we obtain also the alpha enhancement of the galaxy. And here I showed you the relation of the alpha enhancement as a function of the velocity dispersion, and the alpha enhancement as a function of the mass. It is a discussion if there is a linear relation between the alpha enhancement and the mass. For the Atlas galaxies, seems like it's a linear relation. But when you go to the dwarf galaxies, when you go to masses below 9 or something like that, there is a big dispersion. Some of the dwarf galaxies are located in this linear relation, but some of them not. Okay, it's better to do a polynomial fit of second order. So this relation is like a U-shape, basically. Okay, so dwarf galaxies has a high alpha enhancement similar to the massive early type galaxies, but some. We add more galaxies to the sample. Remember that Fornax, we have galaxies from 10 to the 7, 10 to the 9, Atlas between 10 to the 9, 10 to the 12. We went to the literature and we add galaxies from the local group. Okay? In the local group, the masses of the local group galaxies are 10 to the 6, 10 to the 5. So we took stars from the literature in order to analyze, to have the alpha enhancement, the age, the metallicity, etc., etc. This was taking everything from the literature. And when you put all of these samples together of galaxies, here you have the alpha enhancement as a function of the velocity dispersion. So, for example, this is the metallicity, and this is the alpha enhancement. So if you see the metallicity, these are the galaxies from Atlas. The blue points are dwarf galaxies from Coma, from Smith 28. These are Fornax galaxies, our Fornax galaxies. And when you include the local group galaxies, metallicity is going down very, very, very fast. This is the alpha enhancement. Remember, some of the galaxies are located in this linear relation, but the Fornax galaxies, some of them are located in this U-shape. And when you put the local galaxies, they are again going up. It's even more clear, the U-shape between the alpha enhancement and the mass or the velocity dispersion. Even more, we discover a relation between the alpha enhancement and the location in the cluster. Okay? Here we have the local group. This is, of course, the distance to the Milky Way. Fornax galaxies, Virgo galaxies from Atlas, Coma galaxies from Smith. From here to here, there is a factor of 10,000 in mass. This is the local group. This is Fornax, 10 to the 14. And still there is a relation. Okay? So galaxies located in the inner region of the halo, where they are, has larger values of alpha enhancement than galaxies located in the outskirts. Remember that the alpha enhancement is giving us the time scale of the last major star formation event, basically. So what does it mean? That the last major star formation event in these galaxies was earlier than this galaxy. So the environment is doing something in the stellar population, quenching the galaxies earlier in the center of the halos than in the outskirts of the halos. More things that we did. Due to we fitted the spectra using PPXF, PPXF provides us the weights of the different population that is using for the fit of the spectrum. Collapsing these weights, we can produce the star formation histories of the galaxies. And this is what we did. We computed the star formation histories of the different galaxies from the Fornax cluster. Okay? Here you can see this is the star formation history, this rows here, and this is the cumulative mass of the galaxies as a function of loop factor. The star formation histories are very useful because we can compute time scale. We can compute, for example, T50, which is the time when 50% of the stars in the galaxies are formed. We can compute T90, which is the time when 90% of the star population in the galaxies is formed. Usually in the literature, T90 is associated with the quenching time of the galaxies. So T90 is telling us about the time when the galaxy quenches, basically. We put together all the star formation histories. We did also for the Atlas galaxy using the same methodology. And here you have all the star formation histories together, separating in color with the mass of the galaxies. What we have? The very massive galaxies, the star formation history is very quick, let's say. So T50 and T90 occur at high redshift, basically. When we move down in mass, the star formation histories are more complicated, let's say, okay? Because the stellar mass is producing slowly than the very massive. For example, when you go to the 10 to the 7 galaxies here, the T50 is not so high than this galaxy. Okay? Also, we can see, for example, here is the same, the star formation history, but the colors now represent the location in the cluster. Here we have galaxies from Fornax, which are these galaxies here, and from Virgo, because the Atlas galaxies, some of the galaxies from Atlas, they are located in Virgo. Okay? Look at here, it's the opposite here. Galaxies located closer to the center of the cluster, Virgo or Fornax, has a star formation history. The stars are produced earlier than galaxies located in the outskirts of Fornax or Virgo. Okay, so the star formation histories of the galaxies depend on the position in the cluster. More things. What happened with the local group galaxies? We took from the literature, Waits et al. 2014, the star formation histories of the local group galaxies. And in the local group galaxies, the star formation histories is the opposite. Look at this is in mass. More massive has more extended star formation history than less massive galaxies. It's the opposite than the bright galaxies, than the bright and the dwarf. Okay? And here, if you put all together, all the galaxies together, from 10 to the 12, 10 to the 6, you can see that these are the most massive galaxies going down, going down, going down, and suddenly, when you arrive to the galaxies 10 to the 8, 10 to the 6, they go on, representing this change observed in the local. This is a nice picture. Let's see if I can explain you and you understand. So we can collapse and interpolate all the galaxies that we have. And here I showed you the look-back time of the star formation histories as a function of the mass. And I represent in colors the cumulative fraction. So this is the T90 of the galaxies. This is the T50 of the galaxies and the T20 of the galaxies. So the time when 20% of the stellar population is born, 50% and 80%. You can see that there is a U shape, similar as the alpha enhancement. But this U shape is very pronounced up to 10 to the 7, 10 to the 8, and then it's going up for the local group galaxies, and it's going up for the very, very massive galaxies. Okay? In this picture, for example, I show you here the mass of the galaxies as a function of the position in the cluster. In color, velocity dispersion, metallicity, and age. There is no relation between age, metallicity, and sigma and position in the cluster, because the isocontours are perpendicular to it. So basically, for these galaxies, for the age and metallicity and sigma, there is no influence between the position in the cluster and these quantities. But if you put the T20, T50, T70, T90, look at very massive galaxies up to 10 to the 9, more or less, the environment is not influencing in this time scale, because the population of the stars of this galaxy is formed at high redshift, and that's all. When you move to the dwarfs, 10 to the 7, 10 to the 9, there is a relation between these quantities and the position in the cluster. And when you go further down in mass, there is relation in some quantities. For example, in T20, some in T50, but here not, here not. In sometimes there is a relation with the position here, in sometimes not. What is telling you this? This is telling you, I think I have another plot, probably we can see better here. Here we have the alpha enhancement color. This is the alpha enhancement position in the cluster mass. This is the formation of the first 50% of the stars and the formation of the last 50% of the stars, basically. So when you form the first 50% of the stars, galaxies below 10 to the 9, there is a relation with the position in the cluster. Basically, galaxies located down to the center of the cluster or the Milky Way, they have larger T50 than the other ones. But when you go to the second part of the stellar population, the last 50%, there is a relation with the position in the cluster only for the dwarf between 10 to the 7, 10 to the 9, but not for the very massive one and not for the less massive one. What does it mean? That these galaxies has very low mass. They go into the Milky Way. They pass for the first time or something like that. They lose most of the gas, and the other 50% of the stellar population, they have very few gas. And due to they have very few gas, there is no relation between the position of the cluster and the mass of the galaxy. This is not happened for these more massive dwarfs, in which they keep the gas and they pass several times through the center of the cluster. And the last thing that I would like to explain you here is that, as I told you, the star formation history is given us several time scale. And one time scale which is interesting is the T90, which is considered as a proxy of the quenching time. These are example of the star formation history and of the dwarfs in the Fornax cluster, and you can see that there is a variety of different values of the T90. Some galaxies are quenched or were quenched at very high redshift, and some other galaxies were quenched in the more closely in time. Okay, so we can ask ourselves one question: are the galaxies in Fornax cluster they were quenched by the cluster, or they were quenching by preprocessing before falling down into the cluster? So we have to compute two times to answer this question. One time is the quenching time, which is given by the T90, and the other time is the T-infall. The T-infall is the time when the galaxy passed through the virial radius for the first time of the cluster. Of course, in observation, this is very difficult, it's impossible to measure, but we can use simulations and we can use the phase space diagram in order to compute the T-infall of the galaxies according with the position in this phase space diagram. Simulations tell us that the galaxies located in the very down region of this phase space, the T-infall is larger than galaxies located in the external region of this phase space. So, using this, we can say, okay, if the T-infall is larger than the T-quenching, then this means that the quenching happened within the cluster. So this means that the galaxy fall into the cluster before the quenching. If it is the opposite, if the T-infall is smaller than the T-quenching, then the quenching happened outside from the cluster. Using Monte Carlo simulation, taking into account the errors and all of this, we can compute a probability of each galaxy in Fornax to be quenched by the cluster of clusters. Basically, we say that a galaxy is quenched by the cluster if the difference between T90 and T in full is smaller than 0. And computing this for the galaxies that we have, this is the probability of quenching by the cluster, by the environment, as a function of the mass. We add also the Atlas galaxies from Virgo. And you can see that there is a relation. So the very massive galaxies, the probability to be quenched by Virgo is basically 0. And when we move to smaller masses, this probability is going up. Okay? In order to compare this, the small dots that appear here, these are galaxies from TNG50, from simulations. We computed exactly the same, this probability for the T50 galaxy. And it's the opposite, it's this curve here. So there is something in simulations. In simulations, most of the galaxies were pre-processes, were quenched before they fall into the clusters that they are living today. But in Fornax, there is a large fraction, about, you can say, for example, 40% of the galaxies were quenched before to fall into the Fornax. So there is something in simulation, and at least Fornax, this is only one cluster, okay? We have to do this for a large sample of Fornax. This is basically the summary of this of the results about the alpha enhancement and so that I showed you in Fornax. Basically, the relation between the alpha enhancement and the sigma is a U-shape. And this is one of the most important. And the other one, I think, is this about the Fornax dwarf. 36% of them are compatible with being quenched by the environment, and the rest in a pre-processing scenario. What we can do next? This is the situation that we have today about the spectroscopy in the nearby universe. Let's say here I showed you the plot. This is the surface brightness of the galaxies as a function of the absolute magnitude. These are the BCG, bright galaxies, dwarfs, and the ultra dwarfs. With large surveys like Sloan, we have a spectroscopy basically up to minus 17.8, minus 18, more or less. Okay, is these full points here? Okay, we have a spectroscopy, massive spectroscopy basically. But there is a lack of spectroscopy around dwarfs and, of course, about ultra dwarf galaxies. And this lack is what we want to fill with WIF. WIF is a new spectroscopy, a MOSES spectrograph that is in commissioning time for the William Herschel telescope. WIF will provide us a spectroscopy in this region here, where there is a clear lack of spectroscopy that we have today with the massive spectroscopical surveys. Basically, this is WIF. It's in the William Herschel. This is the dome of the William Herschel, and it's under commissioning now. WIF has different modes. It has a large IFU mode. It has a MOSE mode, a mini IFU mode in different resolutions. Okay, between 5,000 and 20,000. The IFU, the large IFU mode, is already commissioned. It's producing data, and we have some data that I am going to show you now. But the MOSE and the mini IFU is now under commission. Basically, WIF is going to spend 70% of the total time of the William Herschel in the next 5 years in order to do all these surveys that we were planning during the last year. These surveys are basically, this line here is just a signal. These surveys in the upper region of this line are related with the Milky Way, and the surveys below this line are related with galaxies. Okay. If you want to know more about WIF, about the surveys, the science, and so on, you can see this paper that we published one year ago. Here I show you. This is one of the configuration of the most of the WIF modes. And WIF will offer a unique opportunity in order to study environmental processes. Okay, one of the surveys that we have proposed for WIF is related with nearby galaxies, nearby galaxy clusters. We have the opportunity to have a spectroscopic deeper than minus 18 in absolute magnitude in a large and significantly statistical sample of nearby clusters. Okay. We can do this due to the large field of view that we have and also the high multiplexity that the instrument has. Different nodes, we will use the MOS mode, we will use the mini eye view, we will use the large eye view for these surveys. Basically, the WIF cluster surveys are divided in three main surveys. One related with the very nearby universe, focus basically on the formation and evolution of the dwarf galaxies in nearby galaxy clusters. Then we have the WIF wide field survey, focus on the evolution of the galaxy properties in the infold region of the galaxy cluster, and the WIF cosmological cluster surveys that will be focused on the evolution of the galaxy properties in the core region of the cluster in a large cosmological period, from redshift 0 until redshift 0.5. This, for example, the nearby cluster survey, we select the surveys from the Rosat all sky survey with a cut in redshift, so they are really very close clusters in the northern hemisphere, and we have a total of about 50 clusters, excluding Coma and Virgo. Coma and Virgo is not in this sample. Here I show you, for example, the limited magnitude that we expect to achieve as a function of the redshift of these clusters. In all cases, we will observe up to minus 16, and for the cluster, for the very close cluster, we will observe until minus 14 or something. This is the signal to noise that we expect to have with the blue arm and with the red arm of the WIF spectrograph, and up to upper magnitude 20, we expect to have signal to noise per pixel about 2.53 basically, and also up to surface variance 22, we expect about 2.5 in signal to noise per pixel. The scientific question that we want to answer basically with this cluster is about the stellar population content of the dwarf, how do interaction with the surrounding environment regulate them, about if the dwarfs are primordial or they are end products of the galaxy transformation in galaxy cluster, pre-processing, what we did in the Fornax cluster, all the study that we did in the Fornax cluster, we can do now with the WIF cluster. Also, we will have information about the internal dynamics of the dwarf, because we will have observed the dwarf with the mini eye view, and also all of this question about the star relation, metallicity, masses, etc. This is some preliminary data that we obtained for the science verification. This is one cluster, Abel 2142. This is the central galaxy of the cluster. You can see here some spectra from WIF. This is resolution 2500, because the IFU has half of the resolution of the MOS. This is basically the blue part, and this is the red part. Well, this is no. These are two spectra. This is the central galaxy, and this is the other galaxy. Here there is a group of galaxies falling into the central part of this cluster. This group of galaxies here, and this is observation also with WIF. And you can see, for example, this is on 3. This is the flux of the LIFU, and this is in O3 that seems like there is a tail of O3. This is at the position of these three galaxies. Okay, there is a tail of O3 here that still we have to confirm because this data was done with the first reduction pipeline, and we want to confirm this with the second reduction pipeline that we have already now. Okay, and this is the thing that we can do with and basically this is everything that I would like to show you today, and I am happy to answer questions. We can speak during the week because I will be here until Friday. Okay. Thank you.
Thank you very much, Alfonso, for the very nice talk. For questions?
Okay, well, earlier in your talk, you saw that for some clusters, you were saying that depending on the absolute magnitude, luminosity, you were saying that the red galaxies dominate or the blue galaxies dominate. How is the completeness affecting that?
In the luminosity function, you take into account the completeness. Okay, you have to scale by the completeness of the spectroscopy that you have. So in this luminosity function, is taking into account the completeness. Okay. With Stefano, we did different luminosity function taking into account spectroscopy and photometry. Okay, and use the photometry using a probability. Using the spectroscopy, a probability that the galaxy is not observed with the spectroscopy belongs to the cluster number. It's another approximation, okay? But in the pure spectroscopic luminosity function, the completeness is taken into account. Because the completeness is going down, of course.
Very related to Borja's question. So you see that in some galaxies, the red ones in some clusters, the red ones goes up and others don't. So is it possible that just the absolute magnitude at which the upturn appears is different in every cluster, and you cannot, for the ones that seem to not go up, you're just not going deep enough?
We don't know because we don't have more examples. Okay, spectroscopically it was observed only in a relative five. But Popeso, what Popeso did in 2006, they collapsed all clusters, okay, and they observed that the upturn started at -18 or something. Okay, so this is a collapse of different clusters, but they didn't analyze individual clusters, seeing that we can do that, okay, because we will have 50 clusters. Spectroscopic luminosity function, and we will see if this upturn change with the absolute magnitude or not. And I hope to understand why some cluster has this upturn, some other cluster not. Is related with the environment, with the large scale environment. I don't know. Let's see. Okay.
Questions?
Most of the, well, some of the results that you have shown to us rely on the star formation histories. How have you tested different codes, or how confident you are?
The star formation history, you know that the big question is the normalization. Okay, we did a methodology. I think we put a lot of careful on the methodology about the normalization of this one, okay? Because if your normalization is very high, then the luminosity function is basically flat. The star formation history is flat basically, and you lost the peaks of the different positions. We didn't compare with other methods because these galaxies were not in the literature. Okay? But with WIF, I hope to have enough sample of dwarfs, especially in some nearby cluster, observed in the literature, and we will compare that. Okay? But we put it a lot of careful in the renormalization of the star formation.
More questions?
I don't know if you have data for this galaxy, for the Fornax galaxies.
Not me, but I know people who, I mean, I don't remember the result, but
Because
some people I know, they study the both galaxies. I don't remember exactly. So it will be worth to look at that. But the point is also regarding, you have studied the alpha over Fi, the alpha element over abundances, using Miles. And then I guess that also you made a multiple fit so that the ages and metallicities that you determine are also related, are taken into account the alpha over Fi, right?
Yeah.
Have you done the same analysis with the IMF?
No, we didn't change the IMF. I think we need a larger sample because the IMF is something statistical. Okay? So we need a larger sample, more than 38 galaxies that we have here. But this is something that it's also interesting to.
Another question now, I mean, just curiosity. You know that these dwarf galaxies used to have the specific frequency of globular clusters. It's like bimodal. You may have a very high specific frequencies or low specific frequencies. Have you checked if there is some, when you were seeing this shape, if there is something correlated with this or not?
No, this is a good question. This is a nice question. No, I didn't check. Yeah, and I don't know if this galaxy has globular cluster measures, but it's a nice, yeah, thank you.
Very interesting.
I have a question about the star formation history of the dwarfs with 10 to the 8 solar masses compared to that with lower masses seems different. And one of the reasons that you suggest is that they are able to retain the gas. Okay, so if you check a different cluster, a more massive cluster or a less massive cluster, that sweet spot in the stellar mass should move, should change.
That's it.
Okay.
Yeah, probably this U shape is, for example, this is Fornax. Fornax is 10 to the 13. If you go to another cluster 10 to the 14 or something like that, probably the U shape will change
To higher masses.
To higher masses. Yeah. But this is not down. It's not. It's not.
But you are expecting that. No? If you see that, then
I am expecting
supports that scenario.
Yeah. I am.
If it doesn't change, then it means it's an open.
Yeah.
Okay. More questions?
I didn't get how do you get the info time for the real galaxies based on the simulation?
It's statistical. Okay. So this is the phase space. The phase space. This is the velocity of the galaxy minus the mean velocity of the cluster divided by the sigma, and this is the position respect to the center of the cluster. Okay. Simulations is telling me the infall time of the galaxies located in this green area, in this greenish, blue, and so on. And you can see the infall times. Okay. So basically, galaxies, for example, located in the green part, this part, the infall times of this galaxy, according to simulation, is 5.4 gigayears. And the galaxies located in this region, the infall time, according to simulation, is 2.2 gigayears. This means that the galaxies here cross for the first time the virial radius of the cluster 2.5 gigayears ago. These galaxies 5 gigayears ago. Now we go to the observations. The observations are the points.
Yeah, you have the same observables.
I interpolate.
Yeah.
Okay.
Great.
Okay. More questions?
Muchas gracias por vuestra paciencia. Bueno, yo creo que